Okay, so Guy has already stated that he was bamboozled by number 10,
Yeah.
correct? Okay, so I want to unbamboozle Guy first. So, I'm guessing you're problem 10, right?
Yeah, 10. I mean, I got up to like 10E, and I think I like just bridged out.
Okay, so let's just start at the big picture, right? So you've got two different masses, one of 0.4 kilograms and the other one at 0.8 kilograms, right? So let's say that you have a situation like this where you have like a large steel ball bearing and you have a golf ball, okay? Much more massive, weighs a lot more. So this actually goes back to even the debate back in ancient Greece with Aristotle. So Aristotle argued that the larger object, more massive one, should fall faster than the lighter one does. Because he goes, well, just lift them up, feel them. Okay, this one feels heavier. You drop it, it should fall faster. And for about 2,000 years, no one actually bothered to do the experiment. Okay? Well, they had other things going on. They had, like, the Vikings invaded England numerous times, and the Romans, and, you know, all this good stuff. And the plague, right? They had any number of things that were going on. So then, Galileo in about 1600, according to the legend, goes to the Leaning Tower of Pisa. He takes a smaller cannonball and a larger cannonball and leans out of the Leaning Tower of Pisa. Voila, he drops them, and miracles, they hit at the same time. It was actually created a stir in the community because it was kind of like almost like at a county fair. And these were people that had studied Aristotle and they knew the thoughts. And people were upset with Galileo because it wasn't so much that he disproved Aristotle, but he did it in a very public manner. So it was like almost like he was mocking them. And people were like, oh man, it's Aristotle. You know, come on, chill out. Okay? But that was the style. And so, but that fundamentally changed how science was done. Because prior to that point, it was called the Aristotelian method of doing science, where you would just sit there and you would come up with well-reasoned arguments. You didn't have to do experiments, because Aristotle didn't trust the senses. And if you think about it, and this is a good thing, your brain has had no direct contact with the outside world. Okay? Everything that you've ever experienced, felt, seen, heard, has been filtered through your senses. And so Aristotle argued that in that filtration process, things can get distorted. So if you've ever seen, hopefully at some point in your lives you've seen like a full moon rising, okay? So when a full moon rises above the horizon, it looks really, really, really big, okay? That looks huge, right? Okay? But then as it goes up in the sky, then it becomes smaller. And so if you were just basing upon your senses, you would think the moon is really, really close when it rises and then it gets further away. It's just an optical illusion. If you take your phone and you take a picture of a full moon on the horizon, as it's on the horizon, and you take your phone 2 hours later when that moon is up above, it's going to appear the exact same size. Okay? It will. It's an optical illusion because you have like a visual markers along the horizon. So Galileo comes along and says, no, you have to do experiments. And so the pendulum swung the other way. And then everybody says, look, we're not going to trust anything just based upon a logical argument. You have to have the scientific proof to back it up. So here's where Newton's 3 laws all come into play. So you've got this big, massive iron ball bearing, and then you have Gary the golf ball. Okay? So we're going to drop them. So this is like the 0.8 kilogram mass. This is like the 0.4 kilogram mass. And so the first law of motion is the law of inertia. All that says is objects at rest remain at rest. So when I drop these, okay, when I let go of them, they both want to remain at rest. Okay? And here's what I want you to remember about inertia. Inertia is a resistance to a change in velocity. The more stuff you have, the harder it is to get it to move. But once it's moving, it's harder to stop it. So, love y'all to death, and I'll drop this golf ball on my hand, okay, from this height, not a big deal. I'm not going to drop this from that height onto my hand, okay? Because this stuff is tough to get moving. But once it's moving, okay, that would really hurt, all right? And force equals pain at the end of the day, all right? So this ball has a lot of stuff in it. It has a lot of inertia. It's hard to get it to move. But once I keep moving, it's hard to get it to stop. So I kind of take you through the stop process. So the first thing you want to do is determine the weight of each sphere. Now remember, weight in a physics class is a measure of gravitational force, okay? If I want weight, I'm asking for force. If I want mass, I'm going to ask for kilograms. So what you should see on your answers to 10A is that the 0.8 kilogram mass weighs twice as much as the 0.4 kilogram mass does. Cool with that? Okay? So there is twice the amount of downward force acting on the 0.8 kilogram mass than there is on the 0.4 kilogram. So here's the first thing I want to realize, is that your gravitational force is directly proportional to the mass. The more mass that you have, the more gravitational force there is, okay? Because there's more stuff that interact, okay? More force, more mass. And that's what I wanted you to see out of that first question that you did when you drew that graph. So on number 1, you should have a graph, and it shows that, oh, the more mass something has, the more it weighs. And you should have a nice little graph that looks something like this, where you have your mass along here, and you have Fg along here, and it should be this nice little sloping line. And oddly enough, that should have a slope of 9.8 meters per second squared. Okay? Here's the basic idea, and this is one of the most important things that you have to get. Mass is proportional to weight. Okay? So don't tell me, oh, gravity is the same for everything. It's not. This is why I had you do these calculations. More mass weighs more because there's more of a gravitational interaction. Now, what I'm getting you then to look at in B, it says, okay, which sphere has more inertia? The only thing that affects inertia is mass. 0.8 kilograms, 0.4 kilograms. A lot more stuff, harder to get it to move. Okay? 0.8 kilograms has more inertia. Okay? Then on C, when you're dropped, what's the value of the force acting on each sphere? So when I drop them, okay, when I let go of this sphere, what's the only force acting on it? Gravity. When I drop this one, what's the only force acting on it? Gravity. Okay? And then basically your answers to 8C are the same as your answers, excuse me, to 10C are the same as your answers to 10A. Okay? Because as soon as I drop it, the only force acting on it is gravity. Okay? Cool with that? Now, what's the acceleration of each sphere when they are dropped? So here's what I want you to see, is that let's say you don't know what the acceleration due to gravity is. If you were to find that answer to D, okay, take your answers from C, divide that by the mass, in this case, like, I hate this pen, 0.8 kilograms. Okay, take that weight on your answer C, divide that by 0.8. Take the other weight and divide that by 0.4. What do you get for each answer? Meters per second squared, but what's the answer? Numeric answer?
Negative 9.8.
9.8. They're both going to accelerate at 9.8 meters per second squared.
Did
Yes?
we need to show work on that? Because I just
No.
put, okay, that's fine. Okay.
You don't. But here's what I want you to see, is that force is proportional to mass. So this thing has a lot more inertia. It weighs a lot more. But it takes a lot more force to get this to accelerate at 9.8 meters per second squared than it takes the golf ball, because this has less stuff. So what I want you to see is that the acceleration of everything in free fall is the same, 9.8 meters per second squared. But it's because their force is proportional to the mass. This weighs more, but I end up with the same acceleration as this. because there's more force, it's proportional to that. So then, the final velocity of each. What you should see on E, and because you know how high they're dropped, so on E, just use that equation. V squared equals, my pen sucks, equals V naught squared plus 2AD. Okay? That's what you got. Now, one of the things you've got to be able to do as we get into more and more complex equations is look at what's a factor and what is not a factor. Could you plug the mass of the dropped object into that equation if you tried? Can't do it, okay? You can't plug in the fact that this has 120 dimples on it, or that this is made out of iron, okay? You can't plug in the density, you can't plug in any of that. So when you look at those kinematic equations, you go back to that ball off the building problem. You know why I never gave you the mass of the ball? Doesn't matter, okay? Does it affect force? Yeah. Does it affect how much force it takes to throw it? Yeah. Doesn't affect the outcome in terms of the acceleration and distance. So what you should see is that your answers to E are the same. They're both going to land with the same velocity. They're both going to end up with the same acceleration. But they don't have the same amount of force. The one with twice the mass has twice the gravitational force. Okay? That's what I want you to see. Got it? Morella?
I have 2 questions.
I only have one answer, so choose wisely.
Okay.
What?
First, G. Because the mass does not affect the velocity and acceleration, it shouldn't affect the height, right? Yeah,
Perfect.
because, okay. And then for E, the question, so it said,
All right,
even though,
let's talk about all of 4.
okay,
Okay? So I happen to have a hydrogen-filled balloon. Okay? And last year it was pointed out that when I hold this, if you've ever seen the movie Up, that I kind of look like the guy from Up. Okay? So that wasn't Up. Anyway, so yeah, I kind of look like that guy. Didn't used to, but I
isn't
did.
that like highly flammable or something?
Oh, very.
Oh, why do we have it?
Ask my Chem 1 students, huh?
Are you gonna light it on fire?
We can maybe. We'll see. Okay. All right. So here's the deal. So I've got this 20-gram mass, right? So the balloon's clearly lifting up on it. Okay, the balloon's applying an upward force on it, right? So why doesn't the 20-gram mass accelerate upward? There's an upward force.
Because the net force is down still.
Yeah. So if I let go of this, it's going to fall. Okay. So, but what's happening is that if I take this off, okay, then the table is providing all of the force to balance out the effect of gravity. If I hook up the balloon, then the balloon is providing some of that upward force. But the amount of downward force is still the same. Okay? So that's what I want you to see on all of number 4. So here's the scale. You have a 0.5 kilogram mass. Okay? So you have a 0.5 kilogram mass, and this reads in newtons. So that scale should be reading 4.9 newtons. So as soon as I hook up the balloon, listen to me very carefully. As soon as I hook up the balloon, what's that going to do to the downward pull of gravity?
Decrease it. Oh no, it's gonna stay the same.
It's going to stay the exact same. Okay, the downward pull of gravity is still, bless you, is still going to stay the same. But what's going to happen to the force that's provided by the table? Will be more or less once I hook up the balloon. Less, because the balloon's helping it out, right? Okay? So it's kind of like this. Let's say I loan Dime $4.90. Okay? Okay? He pays me back $4.80. Okay? So somebody else, Eli for example, will say, hey, I'll make up the difference. He's going to give me 10 cents. So the total amount of money paid back to me is still $4.90. I get $4.80 of it from Dime. Ironically, I get a dime from Elon, okay? I should have switched that around. In retrospect, that would have been a better story. Okay, Eli, you owe me $4.80. Dime, you owe me a dime. Okay, woo! Okay, don't spend it all in one place. Woo! Okay, so here's the deal. But the sum of money that I get back is still the same. So what I want you to see on D, when you're drawing that free body diagram, you should have three forces. So here's the balloon. So you should have a downward force of what? What does a 0.5 kilogram mass weigh? 4.9 newtons. And I would make that negative because we're talking about the sum of these forces. So I got a negative force of 4.9. So what do my upward forces have to add up to? 4.9. So you should have two upward forces, one from the scale, one from the balloon, that add up to 4.9. Yes?
So does that mean that the normal force is going to be 4.8, and that's why it doesn't accelerate, so the net force is still 0?
Yes.
Oh.
That's
That's
why this
weird.
thing isn't accelerating, because everything still adds up equal to 0.
Okay, that makes
Okay?
sense, I think.
Now, however, though, if I take a 10-gram mass and hook it up to a 10-gram mass, okay? So with this one, what's happening? So when I let go of it, it does begin to accelerate. Which way? Downward, but it just barely. If I hook up a 20-gram mass to it, come on, then it drops much faster. So what that tells me is that the force from the balloon is just a little bit less than than gravity pulling down on this. So this is like watching gravity in slow motion. So even if I throw it up in the air, it's like slow motion gravity. Okay? So, kind of a cool thing to watch. Let's talk about number 5. Because if your answer to 5A is wrong, everything else is going to be wrong. Okay? So your answer to 5A should basically be your age right now. Or pretty close to it. Okay? Because if that's wrong, the rest of the problem is going to be a train wreck. So here's what I'm saying on number 5. This thing is going to start off at a constant velocity. So you're going to push this thing at a constant velocity. So what do all the forces add up to? 0. Now, you push it along and you stop. As soon as you stop pushing it, what do you lose?
Applied force.
What's still there? So that's your unbalanced force. So to get your acceleration on C, take that frictional force on A divided by the mass, there's your acceleration. So your acceleration on C, this is an absolute value. You have to decide if you want to make it positive or negative. But your acceleration on 5C should make a fairly decent GPA. Okay? Not, wow, you're a rock star kind of thing, but a respectable GPA. Okay? Especially if it's a non-weighted scale. Okay? Fairly respectable GPA. Now, on D, you need to find two distances. You need to figure out the distance that it's going to travel, pushing it at a constant velocity. Well, you're traveling at 5 meters per second for 6 seconds. So, Jack, how can I figure out that distance?
Distance equals velocity times time.
Yeah, I can go distance equals velocity times time because of the fact that it's traveling at a constant velocity. So that gets me 30 meters. Add that to the distance that it takes to slow down. I would use that equation. So your overall answer on 5D should be in the low to mid 30s. Okay? Now, on that velocity time graph on E, label everything. You're going to label 2 forces and you're going to label 2 accelerations. Let me give you a hint. 2 of those are going to have a value that are 0. 2 of the values are going to be negative values. Okay, so 2 of them are gonna be 0, 2 of them are gonna be negative values. Got that?
Oh.
Your answers to 6, 7, and 8 all should be something times 10 to the third. And your answer to number 9 should be something times 10 to the fifth. So basically what happened on 9, this guy jumps out, happens to land on a big pile of snow. He was in Alaska. And he's going to basically hit the snow going at 53.6 meters per second. The impact crater is 1.07. Those are 2 words I hope are never associated with me. Oh, what was Brookhamp's impact crater? Okay. So anyway, so that answer on number 9 should be something times 10 to the fifth. So 6, 7, and 8, 10 to the third. 9 should be something times 10 to the fifth. And some of those should be negative values, okay? Because you have positive velocities and you're slowing down. So some of your answers on this assignment should be negative values. All right. Anything else?
You move it 1, 2, 3.
Going once.
This is
Going twice.
unless you need 6.
2.5.
There's 4 6 8s on that one.
So, okay, stop you on the camera. Figure out of this class, this concept of net force is going to be like one of the most important. That and like gravitational fields. So, so what I did is I wrote this story, and you all suck at reading, so I'm going to read it to you in a horrible Scottish / British / Australian accent. Okay, kind of depends upon the mood. Okay, so here we go. You do have audience participation at one point. Okay, so
Do we also have accents?
huh?
Do we also have accents?
That's up to you.
Said British?
If you can do boo hiss in a Scottish accent, bonus points.
Boo hiss.
Aye, come on, you like.
Hi, Mr. Birdman.
Let me go get my kilt. Okay, so here we go. Once upon a time in the kingdom of physician, there were 2 opposing forces. One represented the forward-looking people who wanted progress, and they were very positive. The other was the faction that opposed everything that the positive people wanted and were generally considered to be negative. Thus, in the kingdom, there were always a struggle between the 2 forces. The positive people had a variety of tools they applied in their battle. They could push, shove, lift, throw, hurl, heave, and once they discovered mechanized equipment, they started using rocket engines and hot air balloons. Theirs was viewed as a positive force since they were trying to move the kingdom forward. In opposition to such forward-thinking endeavors, there were the negative people who opposed anything the positive people would attempt, and they were negative. That's not bad. Okay. As with the positive people, they too had a variety of tools at their disposal, but they were limited to only 2 tools, friction and gravity. The friction and gravity were generally referred to as the opposing forces and took away from the endeavors of the forces applied by the positive people. In future years, they would become known as the gravity and friction mafia. The negative forces would also only be used in special circumstances. If the positive people were trying to move something horizontally, then the negative people would use friction to oppose the applied force. The more friction there was, the less positive force remained, the more money paid out to the frictional mafia. If the positive people were trying to get something into the air, otherwise known as vertical motion, then the negative people would use the weight calculated by taking mass times gravitational acceleration. The more massive the object, the more money paid out to the gravity mafia. As is true of every epic battle, protocol had to be established to determine who won or lost each battle. After much wailing and gnashing of teeth, it was determined that a mathematical system was to be established where force net equals force applied plus force opposing. Okay, so with all that said, what does it mean? Valid question.
Net force is just force applied plus force opposed.
It's just
That's simple verb,
And
yes.
so if it equals 0.
So let's say that I'm going to take yonder balloon and we'll go back to the little 10 gram mass, okay? So what does a 10 gram mass weigh?
10
How could you
times.
calculate the weight of a 10 gram mass?
mass times acceleration of gravity.
So what are you gonna have to do with the 10 grams?
Oh yeah,
Convert that into kilograms by
converting
dividing by
1,000.
1,000 and then multiply that by 9.8. So if you do that, trust me, you get 0.098 newtons. So I've got a downward force. The gravity mafia is pulling down with the force of 0.098 newtons. Now, when I let go of this, what happens? It falls. So what does that mean about the upward force relative to the 0.098 newtons? Less than. You think it's a lot less? Ish?
It's
Because when I let go, it does accelerate downward, right? But that's nothing compared to just straight gravitational acceleration, right? So I got to figure that upward force is not quite 0.098 newtons, but not a whole lot of different. So what that means is that since this thing is going to have a downward acceleration, that means my upward force, my force applied, is probably going to be a little bit less than 0.098 newtons, maybe like 0.09, something like that. Now, if I change this up a little bit, whoops. You okay? Yeah. And let's say that I put take off that 10 gram, and I'll put on a binder clip like this, okay? Now, if I put on a binder clip, and I let go of it, what happens? Accelerates upward. So now what's happened? The upward force is bigger than my downward force, okay? So if I take that and then I'll put a small little binder clip on it, now that's back to going down. So maybe I take a paper clip. So that's pretty close, right? So what do you think would happen if those two forces were exactly balanced out? It would just hover, right? Okay? So because that downward force is just a little bit less, static electricity has just kicked in, and we're defying gravity. That'll come down eventually. So, okay, there we go. So, that was just going to bug me. All right, so here's what I want you to see. On all of these problems, you're going to go off the idea.
Look, it's not moving.
Huh?
Oh my god, that's so weird. Wow.
Wow.
I'll show it to Jenna.
Okay. So, what I would recommend on all of these problems is that you set up a chart. And you're always going to have three things. You're going to have force applied, you're going to have force opposing, and you're going to have force net. Now, in this situation, okay, when I let go of this, right, and it begins to accelerate downward, that means that if I have a negative acceleration, that means that this downward force might be, say, negative, I don't know, I'm just going to make up a number, maybe negative 1 newton. My applied force then might be 0.90 newtons. So when you talk about net forces, you always talk about the sum of the forces. Okay, you always talk about adding them. So I'm going to take 0.9, add that to negative 1, and I'm going to get negative 0.1 newtons. So what that means is that when I let go of this thing, there is a negative net force acting downward. Now, here's the other thing. Listen to me very, very carefully. It is only the net force that equals mass times acceleration, okay? Not force applied, not force opposing, not force friction, nothing. It is only net force that equals mass times acceleration. So if I want to calculate the acceleration of this system, I'm going to take that net force of negative 0.10 newtons. I just put a new battery in this thing. and then I'm gonna divide that by the mass. Let's say the mass is 0.1 kilograms. So I'm gonna have a negative acceleration of negative 0.1 meter per second squared. Now, I take off the paper clip. Okay? I then let go of it. Now what's happened?
It's accelerating upwards.
So now, when I take off the paper clip, what have I done to my applied force from the balloon?
It stays the same.
That stays the same. It's still the same balloon, okay? So if I take off the binder clip, or the paper clip, then I still have the exact same applied force of 0.90 newtons, right? Now my opposing force became less. Now my opposing force might be negative 0.8 newtons. Now my net force is 0.10 newtons. Now I get a positive acceleration, okay? Now, one thing I want you to get out of your minds is the idea that positive acceleration always means that you're speeding up. If I throw this down, what's going to happen? Yeah, it's going to accelerate. So if I throw this down, it's like an anti-gravitational field. So if I throw this down, I'm going to have positive acceleration, which is going to make it slow down, stop, and speed back up. So this is like gravity in reverse. So I throw it down, it stops, and then it speeds back up. So get out of your mind right now that positive net force and positive acceleration always means that you're going up. It can, okay? But I can also have a positive net force and positive acceleration and be going down, but I would be slowing down as I went. Now, the other great application of this concept is, let's say, for example, I happen to have a helicopter. This is like, why do you teach physics? Because I go to Dr. Botts and go, I need a remote control helicopter. Why? Because I need to teach forces. Okay. So, take off. Whoa! Hold on. We'll try that again. There we go. Okay? So, back up here. Now, that helicopter is just hovering. Okay? What do you know about the forces acting on that helicopter? Two forces are equal and opposite. Now, if I wanted to accelerate upward, what am I going to do? I'm going to apply a little bit of upward force, and I'm going to get some upward acceleration. If I decrease that, come back up there, right? Now, if I just make that thing hover right there, those forces are balanced out. So when I change the throttle, what am I changing? My applied force or my opposing force?
Applied.
Yeah, I'm changing my applied force. So let me see if I can kind of stick the landing. Not bad. Okay. So, let's get this back up. This is why I teach physics. I get to play with toys. So, if I just turn this on and give that just a little bit of a bump like this, okay, why doesn't it take off? I'm applying an upward force.
It's not as strong as the gravity.
So that's just it. So again, this is a classic situation where just because you apply a force doesn't mean that you get an acceleration. Okay? I don't get an acceleration. Now, imagine that helicopter is sitting on a scale. So when I give that a little bit of a boost like this, what would happen to the reading on that scale?
It would go up.
It would decrease. Why?
Because net force.
I'm applying an upward force. Am I changing the downward force?
No.
No, that's still staying the same. So by applying a little bit of upward force, that's just like me holding onto this balloon. If I was sitting on a scale and I hold onto this balloon, the reading on the scale would go down just a tiny bit because this balloon is providing an upward force to me. Okay? Not enough to really make any difference, but it would be a little bit. So there's an upward force, just not enough to get me off the ground. Same thing is true of that helicopter. But if I want to accelerate upward, okay, then that upward force has to be greater than the gravitational force. I know that. Thank you very much. It's like, what do you do after school? I'm working on lesson plans. Really? It looks like you're flying a helicopter. No, that's a skill set I have to have. Okay. No. That would be bad. Okay. So here, there's two classic examples of problems like this. One is involving literally rocket science. Okay? So let's say that we have a rocket, and it has a mass of, I don't know, not very big, 1.02 kilograms, about 2.2 pounds, okay? And let's say that the rocket engines can produce an upward force of, Dime, pick a number between 30 and 40.
37.
Oh, you picked an odd prime number.
30.
No, we're good. Already done. 37 digits. All right? So, here's the deal. We have a rocket with mass of 1.02 kilograms. Dime picked an odd prime number, so there's going to be an upward force of 37 newtons, right? Good with that. Okay? Now, when you get in a problem like this, I beg of you, draw a chart, okay? And you only have three potential things on this chart. You're going to have force applied, force opposing, and force net, okay? Fat, fop, net. That's what you got. Now, is the 37 newtons my applied force, my opposing force, or my net force?
Which one?
My 37 newtons. Is that my
That's
applied, my opposing, or net?
Apply.
That's my applied force. That's what's coming from the engines, okay? It's cool. So I got 37 newtons. Now, what you have to ask yourself is that, do I need to pay off the mafia? Okay, is there any mafia involved in this problem? So, in this situation, what's the mafia that I have to pay off? Gravitational mafia. Because the gravitational mafia is going, and that's nice, you got a rocket, that's cute. You're a good boy, okay? We need you to pay some money, okay? Because if you want to launch, you got to give us some money. So you have to figure out how much money you have to pay the gravity mafia. The gravity mafia charges basically $9.80 per 1 kilogram of stuff that you want to get up off the ground. That's the rate. $9.80 per kilogram, right? So I have 1.02 kilograms. So how can I figure out how much I have to pay the gravity mafia?
Force equals mass times.
Multiply. So somebody take 1.02 times 9.8.
It's not negative 9.996.
So let's just call it negative 10.
I don't
Okay.
like that.
So here's an analogy that you can make, okay? You sell something for $37, but it cost you $10 to buy it in the first place. So what's your net profit? $27, okay? Now, if you take that analogy one step further, okay? So this won't happen, but stay with me here. Let's say Topher's in the lunchroom, okay? And he won't do this, but stay with the story, okay? So Topher sees a freshman with a nice watch, okay? Topher goes up and he goes, "Hey kid, why don't you give me the watch?" "Yes, sir." So Topher just takes the watch from the freshman, brings it into class, it's sitting there on the table. Preston sees it. Preston goes, "It's a nice watch." Preston, and Topher goes, "Yeah." He goes, "Would you sell it?" "Yeah." "How much do you want for it?" $37. Preston goes, "I think that's valid." So Preston's going to pay Topher $37. What's Topher's net profit? $37. Why? He didn't have to pay anything for the watch. Okay, so he sells it for $37 because it didn't cost him anything to get the watch. Now, Topher wouldn't do such a thing. Here's a better scenario. Topher's in the lunchroom and he sees a kid, little freshman, down on his luck. He goes, "Hey, what's happening, kid?" He goes, "I forgot my lunch money." Topher goes, "You got a nice watch." He goes, "Yeah." Topher goes, "I'll give you $10. You get to have lunch. I get the watch." Okay, legit. Okay? So Topher walks in, he's got the watch, Preston pays him $37. Now what's Topher's net profit? $27. This is what's happening here. Okay? So it cost him $27. Excuse me, he has a net profit of $27 because it cost him $10 and he sold it for $37. Now, let's say Topher goes being the nice guy that he is. He goes to the kid, he goes, "Hey, I'll give you $37 for the watch." Kid goes, "Okay, legitimate, all right." He sells it to Preston for $37. What's his net profit? Nothing. Is Topher's checking account going to accelerate? No. Why?
Because net is
Didn't make anything. There's no net change in anything, right? So here's the deal. So every problem that you're going to work from here on out is going to play out one of two ways. Either Topher is going to sell the watch for a profit or a loss, and his account is going to accelerate, or he's going to sell it for the same amount of money that he paid for it, and there's going to be no acceleration. So literally, every problem you're going to have from here on out is going to be one of two things. Either the net force is going to equal to 0, and you're going to have no acceleration, or the net force is going to be a non-zero value, and you're going to begin to accelerate. That's it. There is no other type of problem that I can give you. Literally, every situation from here on out, every problem is going to be one of two things. Either you're going to have an accelerated motion and the net force doesn't equal to 0, or there is an accelerated, or there's a constant velocity and there is no net force. Now, pay attention. So let's say, for example, I take this set of weights and I push it at a constant velocity. If I'm pushing it at a constant velocity, are there forces involved? If I push it at a constant velocity, are there forces involved?
Yes.
Oh, for the love of all things physics, yes, I'm pushing it. There's friction, there's gravity, there's the normal, okay? There are all sorts of forces acting on it. But they will all add up to 0. Now, as soon as I stop pushing it, what's going to happen?
It's going to accelerate.
It's going to accelerate. Now, this is a situation where the frictional mafia is involved, okay? So if I push this thing at a constant velocity, I'm paying off the frictional mafia, okay? And as soon as I stop pushing it, the frictional mafia basically says, "You don't want to pay us any money? We're going to make you stop." Okay? And that's why it stops, because the frictional mafia says, "Hey, nobody rides for free, Jack," right? You don't want to keep pushing it? We're just going to shut you down. And that's what happens. So, you have two different types of mafia. You have the gravity mafia, you have the frictional mafia. So if something's going up, you have to pay off the gravity mafia. Unless I explicitly tell you that you are in deep space and the effects of gravity can be ignored. If I do not tell you that, you assume that you have to pay off the gravity mafia. So unless I explicitly, and I mean explicitly say, the effects of gravity can be reasonably ignored, you pay the gravity mafia when you're trying to get something in the air. Okay? Got that idea? Okay. So now, if I were to drop the ball, here's my net force of 27 newtons. Now, if I want to calculate the acceleration of the rocket, so I'm going to take 27 newtons and divide that by 1.02 kilograms. What'd you get? 26? So I'll call it 26.5 meters per second squared. Okay? So that's going to be the acceleration of the rocket. Now, here's the deal. If you're an engineer, if you were literally doing rocket science and you're a rocket engineer, the rocket scientist, let's play the what if game. What if we could shrink the mass of that rocket? We're going to develop some lightweight materials. And we're going to shrink the mass of that rocket to 0.92 kilograms. Okay? I'm going to decrease the mass of the rocket at 0.92. What's that going to do to the applied force from the engines?
Nothing.
Maggie?
It's not gonna change it.
I'm not going to change my applied force. The engines are still going to kick out 37 newtons of force. Okay? That's not going to change. Okay? That's still 37 newtons. But what's that going to do to my opposing force? Ah, that's going to become much less. Now, somebody take 0.92 times 9.8.
9.08.
What'd you get?
9.02.
9.02? Quit. Now, an interesting thing happens. Negative 9.02
C.
newtons. So if I decrease the mass of the rocket, what's going to happen to my opposing force? It's going to become less. This is like Topher paying less money to the freshman. Topher went from paying $10 to $9. So what's going to happen to Topher's net profit? It's going to go up, right? So Topher's now going to be making, so if you take 37 newtons minus 9, you're going to get, or 9.02, what do you get?
27.98.
So what's happened to Topher's net profit?
Paid 98 cents.
Yeah, his net profit has gone up. Now here's an interesting thing that happens. Not only does he have a bigger net force, he also has less stuff to accelerate. So instead of dividing by 1.02 kilograms, now I'm going to have a bigger net force, but I'm going to be dividing it by even a smaller mass. So what's that going to do to the acceleration?
Increase it.
Make it go up. So this is why, like if you go back and study like the Apollo missions to the moon, they paid engineers huge sums of money if they could find a way to reduce the weight of the rocket. Because if they could reduce the weight of the rocket, because you can't change the force from the engines. That's a fixed value, okay? You can only get so much force out of the engine. So if you could reduce the weight of the ship, that provided a smaller opposing force, you got a bigger net force, and then you had less stuff to accelerate, and your acceleration became even greater. But that becomes like a catch-22 with rocket engines. So everybody says, oh, well, let's just build bigger rocket engines. Well, that's cool. But what's the problem with building bigger rocket engines? They weigh more. They have more mass. They have more inertia. Guess what? More rocket engines take more.
Gasoline.
Yeah, they take more fuel, right? So then it becomes this catch-22. It's like, oh, let's build bigger rocket engines. Fine. Let's build bigger rocket engines. Guess what? You got to feed the beast. You got to carry more fuel on those rocket engines. Well, if you don't get enough acceleration from increasing the size of the rocket engines and the added fuel, there's no point. So that's why if you're a rocket scientist, you live and die. You wake up every morning and you go, force applied plus force opposing equals net force. And the only thing you can really control is that opposing force, and you want to decrease that mass. Got that idea? Okay, so stop that, stand up, take a quick stretch. Time to deal with the gravity mafia. And now we're going to deal with the friction. So one way you can think of friction is that in some ways it's like horizontal gravity. And as odd as that may seem, so like if I give this a throw, it slows down and then it comes to a stop and it changes direction. Well, if I give it a push, it stops. It just doesn't change direction, which would be really weird. It's like you push something, it stops, and then it comes back. It's like, oh, kind of cool, right? So friction, in some ways, can be modeled just like gravity does, okay? Now, if there's no gravity and I throw this thing up in the air, what's it going to do? It's going to keep going. So I can do the same thing with friction. So if I take this and I give it a push, what happens? It stops, right? However, if I turn it into a hovercraft and I give it a push,
Wow.
What does it do? It comes back, right? Okay.
Can you do it again?
Oh wait, let's show Jenna.
Let me go to the back. So stand up, sheet.
That's exactly like that.
Okay?
Yeah, well, yeah.
So, this is the classic example. Now, if I try and do that with it off, that's cool.
That's embarrassing.
Oh, I know. So, what's the fundamental difference between the two? Friction. So when it's on, I've eliminated that frictional force. Oh, give us a kickback.
Oh no.
Oh, point. Thank God. Okay, so if I turn this on, basically I've eliminated the frictional mafia. That would be like me throwing this up in the air if there was no gravity. So when I turn this on, basically it's a perfect inertial system. This thing is going to keep going in a straight line until an outside force acts upon it. Since there's no friction, it's just going to keep going and going and going. So, but if there is friction, guess what? It comes to a stop. Got the idea?
Yes,
Okay,
sir.
back we go.
Money. Did you say you hate me?
Okay,
Wow.
so
I got that on video. She said she hates me.
No, I was kidding.
Let's roll. I'll roll to the tape later.
okay. So situation number one. I've got a mass with 1.02 kilogram, and I'm going to apply 10 newtons of force to it, and I want to calculate the acceleration. Okay? Now, I have not given you anything about friction, opposing forces, nothing. So, for lack of any other information, if you set up that chart, and I swear to you, and I'm not going to do this just to be a jerk, but if you come up and you say, Mr. Burkamp, I don't know how to do this problem. Here's the first thing I want to ask you. Do you have a pen that can write? Because I don't. And then I'm going to ask you, have you drawn a chart showing all the forces? Force applied, force opposing, force net. So in this case, I have an applied force of 10 newtons. Do I have an opposing force?
Yes. Wait, no, you
You
don't.
don't have any friction.
I have given you nothing,
You said
right?
no friction? Oh.
Yeah.
I haven't given you the coefficient of friction. You don't know what the frictional force is. Nothing. So you have to assume that there is no opposing force. My net force is 10 newtons. I'm going to take that 10 Newton force. I'm going to divide that by that mass of 1.02 kilograms. And I'm going to get a horizontal acceleration of 9.8 meters per second squared. Okay? If there is no friction, all of that force goes to accelerate the box. However, let's say there is friction. So let's say that I give you the coefficient of friction is actually 0.100. So mu is 0.1. Now we're going to change the dynamic. So I've still got an applied force of 10 newtons. If I take 1.02 times 9.8, I'm going to get a downward force of negative 10 newtons. I've got a normal force of 10 newtons. So if mu is 0.1, how can I find my force friction?
An equation.
Well, you know that mu times force normal gets me
Force of friction.
force friction. And that's an absolute value thing, right? So if I take 0.1 times 10 newtons, I'm going to get 1 newton. So my frictional force is going to be negative 1 Newton. So this is a situation where Topher paid $1 to the freshman. He sells it for $10. What's his net profit? 9. So now I gotta pay off the frictional mafia. So in this situation, if you set up that chart, you'd have an applied force of 10 newtons. I've got an opposing force of negative 1 Newton. I get a net force of 9 newtons. Okay? There you go. Then I can take that, so somebody take 9 newtons and divide that by 1.02 kilograms. 8.82 meters per second squared. Now, interesting thing happens. What happens to my acceleration when there's friction? It decreases, okay? Has anybody ever tried to drive your car, you set like the parking brake, and then you forget to release it and you try and drive? Anybody ever do that?
Oh yeah, I've done that
Okay,
at an
what
intersection once.
What happens?
Why is your parking brake on in an intersection?
Just don't worry about it. Okay. Nothing.
Okay? Or
You just sit there and it's really
tough
awkward.
to get to move at all, right? Because, or if you've ever seen athletes, like some people when they're trained, like you've ever seen some athletes will run like a parachute stuck to their back, okay? Why are they doing that? Resistance. They have an opposing force that they have to overcome to accelerate, okay? Makes them work harder. So, now let's talk about one more scenario. So, let's go back to the rocket. So we can have gravity mafia, we can have frictional mafia. They're both trying to oppose the motion. Now I want to look at two different situations. Here's our rocket. We were initially applying 37 newtons of force against a downward force of negative 10 newtons. We fired the rocket engines, right? Now, I'm going to fire the rocket engines, but then I'm going to shut off the rocket engines. So that's like me letting go of this ball bearing. As soon as I shut off the rocket engines, or as soon as I let go of this ball bearing, what's the only force left acting on it? Gravity. So if you shut off the rocket engines, or if you throw something up in the air, what does your applied force become? You have no applied force. What's the only force left acting on it?
Gravity.
Gravity. Okay? Just like if I push this and I stop pushing it, what's the only force acting on it? Friction. If I throw this up in the air, what's the only force acting on it?
Gravity.
Gravity. Okay? So that's what you want to be able to think through. You go, okay, what's the scenario? And this goes back to this Jedi Stouffer walk. Stop the force and watch. If you stop a force and watch what's going on, does it accelerate? If it does, that means that there's some external force acting on the system. Okay. Okay. So let me give you some hints on this assignment.
I need it.
So number one, you got a semi traveling at 108 kilometers per hour, and it's going to stop in a distance of 58.5 meters. Okay? So is the truck going to accelerate?
Yes.
Yes. What are you going to have to do with the kilometers per hour?
Put it into
Just a second. Do you have a time? No. What are you going to use to find your acceleration? That equation.
That
Do you know F equals ma?
No. Just kidding, yes.
Yes.
I was kidding, that was a joke.
Okay? So if you can find the acceleration,
That was a really funny joke.
and you know the mass, you can find the force. So the force that's stopping it, is that your opposing force or your applied force? Your opposing force. And since there's no applied force, your opposing force is your net force. Okay? Now, when you get to number 2, what's the coefficient of friction? Mu equals force friction over force normal. You just found the force friction up in problem number 1. Divide that by the weight of the semi, There's your coefficient of friction. What are the two most important words in problem number 3? Constant velocity. I have no idea what that noise is, but it's disturbing. So, on number 3, you have a constant velocity. What do you want all the forces to add up to? 0. Number 4 is the easiest problem on the entire assignment. Okay? I'm going to apply a 18 Newton force to a 1.5 kilogram box that's at rest. Did I give you any information about friction? No. So on number 4, just use F equals ma. That force is the net force. You have the mass, find the acceleration. Number 4 is the easiest problem. Do not screw it up. Now, on number 5, we're going to change the dynamic. So what's the difference between number 4 and number 5?
It's, there's friction.
Now you got to pay the frictional mafia. So on number 5, you have to figure out the frictional force. I've given you mu. When you get to number 6, you're going to have to draw 2 diagrams on another sheet of paper with a ruler and a scale. Okay? So what that's going to look like, I'm going to tell you right now. So here's this box. You're going to apply an 18 Newton force in one direction. I don't care. Okay? You're going to have some frictional force in the opposite direction. You're going to have gravity. And you're going to have some force normal. Set up a scale. You want to draw this with a ruler. Okay? That's what I said. Maybe you're going to, since this is 18 newtons, don't let 1 centimeter equal a newton, or you're going to have this big, long, 18 centimeter long vector. Okay?
No kidding.
So you're going to draw it as a free body diagram like this, and then you're going to draw it tip to tail. Because you're accelerating, when you draw it tip to tail, where are you not going to end up? At the origin, which means you're going to have a resultant, and remember you draw the resultant from the origin out. When you get to problem number 10, you have an applied force of 129 newtons acting on a 5 kilogram rocket. So, over here, and here's what's the difference on 10A. On 10A, I just want you to make a sketch. 10 does not have to be drawn to scale. Draw a rocket, or dot, whatever. And you're going to draw the forces acting on it, you're going to draw some acceleration vectors, and you're going to draw some velocity vectors. So you're going to fire this rocket for 12.6 seconds. Then you're going to shut off the rocket engines. So as soon as you shut off the rocket engines, what's the only force left acting on the rocket? Gravity. What do you think the acceleration caused by gravity is going to be? Negative 9.8. So on the back side on E, there's a whole bunch of things that you need to do. And if you want to draw them here, that's cool. If you want to put them on another sheet of paper, that's cool. You're going to draw me 3 velocity vectors, an acceleration vector, and a force vector as this thing is approaching the top. And then you're going to draw velocity vectors, acceleration vectors, and force vectors once it starts to fall. On the velocity time graph, you have to draw a velocity time graph for the entire time. Keep a running clock. And there's a whole bunch of things that you have to label. If your velocity doesn't fit within this, like if you need a velocity of 400 meters per second, don't go, man, Bergkamp screwed up, man. Your graph is all wrong. What a schmuck. No, okay? If your data won't fit on this graph, don't go, man, Bergkamp, dude, you're old. No, I'm not. Well, not too bad. This is chemistry, right? Okay. Then you got some questions to answer on that. I'm done. You're on your own.
Are we gonna blow the balloon up?
Yeah, we'll blow up the balloon.
Let's go over there.
So,
We can show Jenna this too.
lights on, lights off. Okay, up a little bit higher.
Am I in with way?
Okay. Ready?
It'll be loud.
Little acceleration. Still.